All right, welcome everyone to your notes on impulse and momentum. So this is going to be a new unit, so this is all going to be brand new information to everyone. So first let's define momentum. So momentum is going to be defined as inertia in motion. Now, the way we measure an object's inertia is by measuring its mass. And the word inertia itself is the resistance to change in motion. So objects that have a larger mass have more resistance to changing their motion. It's harder to speed them up. It's harder to slow them down. And when those objects are in motion, that's what we call their momentum. So momentum is going to be given the variable p, and mathematically it's very easy to calculate. So momentum is just going to be mass times velocity. Now, mass is a scalar quantity, velocity is a vector. So when I take a scalar times a vector, I get a vector as a result. So momentum itself is also going to be a vector quantity. So let's think about impulse as being the change in momentum. So let's look at Newton's second law. So we know that the net force divided by mass equals acceleration. And we also know that acceleration is a change in velocity over time. So this is Newton's second law. And this is really just our basic definition of what acceleration is. So if I set those two things equal to each other, right, force over mass equals a change in velocity over time, and then I cross multiply, on the left-hand side I get this thing force multiplied by time. And on the right-hand side, I really get the mass times the change in velocity. Right? Remember, we had a delta V over here for a change in velocity, so mass times a change in velocity. This quantity over here on the left, we're going to call impulse. So an impulse on an object is a force that's exerted over a certain time period, and when you multiply those two things together, that's how you calculate the impulse. And the impulse equals the change in momentum. So my units for impulse, right, force multiplied by time is newtons times seconds. The units for momentum, mass times velocity, that's a kilogram times a meter per second. These units are equivalent, right? A newton is actually a kilogram times a meter divided by a second squared. So if I multiply a newton by another second, I lose the second squared on bottom on the other one. So those are the units, and those are both mean the same thing. And so again, we're going to define momentum as inertia in motion, or mass that's moving. Let's look at an example problem. So I have 100 kilogram balls dropped from a height of 2 meters above the floor. It rebounds vertically to a height of 1.5 meters after colliding with the floor. Find the momentum of the ball immediately before it collides with the floor and immediately after it rebounds. Determine the average force exerted by the floor on the ball, and assume that the time interval of the collision is 0.01 seconds. So we'll assume that the ball is in contact with the floor for only this fraction of a second. Now, let's take a look. So, first of all, I can use energy to figure out what the speed of the ball is, right? We know it's a 100 kilogram ball dropped from a height of 2 meters. So initially, all the energy is potential energy. And we know that from conservation of energy, when it reaches the ground, all that potential energy gets converted to kinetic. So if I let my mgh, my potential energy, equal the 1/2 mv squared, I can find the velocity of the ball right before it hits the floor. Okay, so this ball is going to be moving 6.26 meters per second right before it strikes the floor. I could do something similar, right? I could also use energy to figure out what the velocity of the ball would be after the rebound, right? So it's 6.26 seconds right before it hits the floor. It's 5.4 seconds right after it leaves the floor, right? And again, I'm just using energy to figure this out, but we know that it's going to rebound to a height of 1.5 meters. So the kinetic energy it leaves the floor with gets converted to potential energy. That's 1/2 mv squared equals mgh again. But now we're just using a different h, right? We're using this h prime, the 1.5 meters instead. So this is the speed right before it hits the floor. This is the speed right after it hits the floor. And we know that it took a force in order to change the speed, right? And even more importantly, you have to realize that this speed was going down, this speed is going up. So really, these signs need to be opposite, right, if we're talking about velocities. So let's look at the momentum before. The momentum before is the mass times the velocity. Now, since this is moving down, I'm going to call it negative. So I have the mass times a negative 6.26, and that gives me a momentum of negative 0.626 kilograms times meters per second. And then the momentum after, the same thing, but this time I'm going to call the velocity positive because it's moving back upward. Okay, so that's part A, right? Find the momentum of the ball before it collides and right after it rebounds, right? So before it collides and then right after. Last thing was determine the average force exerted by the floor on the ball. So to change the direction of the ball, a force had to be exerted, right? We had an acceleration here. We had a change in velocity. So I know that the force times time equals my change in momentum. This is my impulse equals the change in momentum. plug in what I know here. I know the time it was in contact with the floor. I know the mass of the ball. I know the change in velocity. Notice that extra negative sign here because this was going down. So this is final minus initial. And I get a force of 116.6 newtons. So the floor exerted a force of 116.6 newtons to rebound that ball back up in the other direction. Now, since we know that impulse is force times time, we could also figure out what the impulse of an object is from a force versus time graph, right? So let's say that this force is being exerted on an object over this time interval, and the force starts off low, it peaks, and then it comes back down low again, right? This might be our ball bouncing off the floor, right? It first hits the floor, a little bit of force, the ball kind of deforms on the floor and then pushes up, and at this point the floor is exerting a maximum force on it, and then it drops back down. Well, force times time, that's this axis multiplied by this axis. So what I'm looking for then becomes the area under the curve. So on a force versus time graph, the area under the curve is the impulse, and the impulse is also equal to the change in momentum. So what about during a collision, right? So let's consider two objects that are colliding together. Collision problems are going to be very common for momentum problems. So if you see a collision, it's probably a momentum problem. So what happens when these two things collide, right? So this cart's moving to the right, this cart's moving to the left, there's a little spring in between them, and when they collide together, they're going to kind of stick together for a second while that spring gets compressed, and then they're going to push away and go the other direction, right? So, okay, now Newton's third law says that a force that one object exerts on another, there's an equal and opposite force back on the first object. So M1 is pushing on M2, M2 is pushing on M1, that's what causes them then to go the other direction. Now, during this collision, the time that they're in contact, the time that the force is being exerted is the same, right? They're in contact for the same amount of time. One can't be in contact with the other longer than the other one. That wouldn't work. So we know that the forces are equal and opposite, right? So F1, the force of object 1 on object 2, equals negative F2, the force of object 2 on object 1, and we know T1 and T2 are equal, right? So therefore, then their impulses must also be equal on each other, but they are in opposite directions. So we have a negative sign there. So if the impulses are equal, that must also mean the momentums are equal, right? So if the impulses were equal and opposite, the momentums must be equal and opposite, right? Remember the definition of momentum here, mass times my change in velocity. And I'm sorry, this actually says momentum 1 equals negative momentum 2. It's also the change in momentum are equal, just the delta sign's not here. So the change in momentum of object 1 equals the negative change in the momentum of object 2. I know that this delta V1 is really a final velocity of object 1 minus the initial velocity of object 1. I know this delta V2 is the final velocity of object 2 minus the initial velocity of object 2. So V1 and V2 are the final velocities of object 1 and object 2. V01 and V02 are the initial velocities of object 1 and object 2. I can distribute these masses out. All right, and then I'm going to switch these terms over here. So I'm going to take this M1 V01 and move it over here, take this negative M2 V2 and move it over here, and what I wind up with is this. M1 V01 plus M2 V02 equals M1 V1 plus M2 V2. Let's take a look at that. What does this mean? Well, this is the initial velocity of object 1. So here, this term is the initial momentum of object 1. This is the initial velocity of object 2, so this term here is the initial momentum of object 2. Over here, this is the final velocity of object 1, so this is the final momentum of object 1, and this is the final momentum of object 2. So the sum of the momentums before equal the sum of the momentums after, right? That's kind of the cool part there, right? So the total momentum before of a system equals the total momentum of a system after. This is called conservation of momentum. Whatever momentum we start with, we need to end with that same amount as well. So momentum is conserved, right? In the absence of an external force, the total momentum before the collision is equal to the total momentum after a collision. And there's just a little problem here of this truck kind of colliding with this car. You're given a mass and a speed of the truck. You're given a mass and a speed of the car. And so from that information, we can figure out, well, what's the total momentum before? Well, the initial momentum of the truck is 2,500 kilograms meters per second. The initial momentum of the car was 800. I've got a total initial momentum of 3,300. After the collision, now I've got a new speed, right? So the truck was going 5 meters a second. It collides. The truck slows down a little bit, right? The car was going 2 meters a second. Now it's going 4.5. It got a little boost, so it sped up a little bit. Again, now we find the final momentums of those two objects, and we add them together. And sure enough, the initial momentum and the final momentum are the same. Now, we can have different types of collisions, right? So and it's going to kind of change how the equation might look for you. Overall, this top equation right here is always true. The total momentum before equals the total momentum after. But down here, I can have different variations of what's going on. So in the first one, I have two initial objects that are moving, and I have two final objects that are moving, right? So this is where two objects collide and they don't stick together. They basically bounce off each other, right? Two individual momentums to start with, two final momentums to end with. They did not stick. The second equation here, I have two initial momentums, but I have one final momentum. Well, how did that happen? Well, that means that those two objects collided and then they stuck together, right? But again, still the initial momentum needs to equal the final momentum. And then down here I have this final thing where here I have a initial total momentum, right, that then breaks apart into two final momentums. This could be where an object breaks into two other objects. Maybe I have one object that explodes into two pieces or something, right? So it would look more like that. Nonetheless, this is still the governing equation that makes everything true, conservation of momentum. Now, during these collisions, they can either be elastic collisions or inelastic collisions. We'll go over examples and stuff where you see the difference between those two. For right now, you need to memorize this. Elastic collisions, kinetic energy is conserved. There's no friction, there's nothing that takes energy away from the system, so the total amount of kinetic energy you start with is the same as the amount of kinetic energy you end with. In an inelastic collision, the kinetic energy is not conserved, right? So kinetic energy is different to start with and end with. Now, in both cases, momentum is still always conserved, okay? But just sometimes kinetic energy is, sometimes it's not. It depends on if it's elastic or inelastic. Let's take a look at one more example. I have a bird perched on an 8 centimeter tall swing, has a certain mass, and the base of the swing has another mass. Assume that the swing and the bird are originally at rest, and the bird takes off horizontally at 2 meters a second. If the base can swing freely without friction around the pivot, how high will the base of the swing rise before its original level? So how many objects do we have before the action? Well, I have the bird and the swing, and they're both sitting still, right? So I'm basically going to say this is all just one object. After the reaction, I have two objects, right? The bird flew off in one direction, he pushed the swing back in the other direction. So the initial momentum that I have has to equal the final momentum. This is conservation of momentum. The initial momentum is actually 0, right? Here's my total mass, but it started off at rest. So the initial momentum is 0. Afterwards, right? So I have, this is going to be the mass of the swing times the speed of the swing, which I don't know. And then I have the mass of the bird times the speed of the bird, which I do know. And I can solve for the speed of the swing. It's going to be a negative 0.68 meters per second. That negative sign coming because he pushed the swing to the left. Now, it asks how high is the swing going to go, right? Well, we know the speed of the swing, and I can then use energy to figure out how high it's going to go. So the initial energy is going to be kinetic, right? So the bird pushes it, the swing is moving, it has an initial velocity given down here. The final energy is going to be gravitational potential, right? At the height of the swing, the velocity is 0. So 1/2 mv0 squared equals mgh. My m's cancel. I can solve for h. I want up with a height of 0.024 meters. Okay, here's one more real quick. So I have Granny on some skates. Granny whizzes by and picks up this kid, right? So initially we've got momentums for two objects. At the end, these two objects stuck together, right? So initially there are two objects that end up with one. The initial momentum before needs to equal the momentum after. So I have the momentum of Granny right here. I have the momentum of the child right here, which happens to be 0 because the child's at rest. And then I have the total momentum of them together that we can assume is one object. And we just add their masses together when we do that. So the final velocity, if we do the math here, winds up being 4 meters per second. Okay, now because momentum is a vector, we can have collisions in 2 dimensions, and the momentum in the x direction is going to be conserved, and the momentum in the y direction is going to be conserved. I will do a separate video to go through and show you this example where we deal with vectors and we have to break things down into components.